Welcome, ladies and gentlemen, to the second episode of the GOM webinar Software Triology. My name is Hagen Berger, and I will show you today the deformation analysis with GOM Inspect Professional. For questions and answers, Markus Meller will support me, so if you have any questions, just use the question and answer functionality. What do you have to expect today? I will show you the point-based deformation analysis. Therefore, we talk about point components, about alignments and rigid body motion compensations. I will show you vector fields, everything about new features, timeline and stage ranges. And we also do some example checks like a projected point distance, absolute and relative angle change, what's the difference, 6-degree of freedom analysis, 2-coordinate system distance, and very nice functionality, the trajectories. Of course, we will also talk about the reporting inside the software. So now I will just change to the software. This is GOM Inspect Professional, and I will simply use stage files from a version 6 project. I just drag and drop the stage files into the software, and the software will now import all these stage files and create a stage project out of the files. You can already see that we have here the skin deformation to be able to evaluate deformation projects. And what you see now is here the entire project inside the new GOM version 8 GOM Inspect Professional software. You have here the timeline, and if you go through the stages with the mouse, for instance, you can directly see what happens inside the project. In this case, we have here the time displayed in seconds on the timeline, but we can easily, with a right mouse button click, change this to index. That makes things much easier to interpret the data afterwards. You can see here we have 145 stages, but we don't see any reference points at the moment. We've done this on purpose because for deformation projects we want to have every reference points with the same ID throughout all the stages. And we achieve this by creating so-called point components. How do we do with this? We go to Construct, Component, Point Component. We click there, and all of a sudden you see that the software recognizes all the points that we have sticked onto our object as reference points in 3D. Now all we have to do is we go over here and enter a name, for instance the bucket, and then we just select the points on the bucket, and all those points will be placed into this dialog over here. I can simply click here OK, and I got the component bucket created with those points over here. I will do exactly the same for the extension arm. We have all the different selection tools available. Put those in there as well. The next one is going to be the boom. Once again, select those points, create. Then we have the superstructure. And as a last component, we have the undercarriage. What you can see here already is that we have targets sticked on the object, but this one is not recognized as a reference point. If you know that this is a real target, you can simply push Control and the right mouse button, and the software will jump automatically from the left camera image that's always displayed in the software to the right camera image, and it draws an epipolar line in there. Here we can see this is a real measuring point. Once again, Control and right mouse button, and this point is also recognized in the group of points of the component. We will do the same for this point here as well, and now we have all those points grouped into the same component. You might have already seen that we have different component types available. all the components that I've used over here are rigid components. We also have deforming components available. So what does that mean? If I open the expert parameters over here, you see that every component has a minimum number of identification points. If you have enough points, it will always say, okay, I have to find at least 5 points as identification points. If your component only consists of 4, of course 4 or 3 is the minimum number of identification points. The component has to exist of at least 3 points. It's better to have more points in a component. So what's the difference now between rigid and deforming component? If you have a rigid component, the identification threshold is a fairly low number. That means the relative motion of the component points to each other must not exceed this limit that's given here inside the identification threshold. That's only valid for rigid components. If we switch to a deforming component type, you can immediately see that the identification threshold gets much bigger. This number that you see over here is the shortest distance of 2 points inside this component. All right, that's the difference between rigid and deforming component type. I will stick here to rigid component because all the components that we have here are not deforming that much. It's absolutely okay to use rigid components. Now, since the automatic recalc is activated, the software goes now through all the stages. In this case, I have in this project 145 stages, and computes all the reference points, identifies the structure of the components, and identifies therefore the components in all the different stages, so that I can work with every component throughout the stages. That means if the software is finished, all points in my project have the same ID over the entire project. You can see this very nicely over here. If I flip through the stages once again, you can see that all points are found throughout all stages, and points that are not bound into a component are not there anymore, so they're not disturbing us anymore. So one thing is that we now have only the sensor coordinate system available. This is the coordinate system that you get from the sensor due to the calibration process. This is the initial alignment that we have inside every deformation project. Of course, if I turn off the image mapping and turn this around a little bit, you can see that this coordinate system doesn't help me to interpret my data. I will go back to the image mapping. What I'm going to do now is I will just use cut data or meshes to align my data to a certain coordinate system. Therefore, I simply drag and drop a mesh from the undercarriage. In this case, I want to have this as a cut body in here. I click OK. And now this cut part is imported to the software. We can see immediately we have now a much better coordinate system. If we take a look at the cut part, the problem is, of course, that we have to align our components to the cut data. To do this, I will just hide the cut data in here and go back to the image mapping, because I can use this now for the alignment. Therefore, I will use the picture-in-picture functionality over here and simply drag and drop my cut file in there. So, got my cut file in here. I will make this a little bit bigger. I have this one in here. And what I do next is I simply go to iAlign and create a 3-point alignment. Of course, if you don't have any cut data or meshes available, you can also use simply 3-to-1 alignments or best fit alignments by reference points. In this case, we will do the 3-point alignment. We have this dialog over here. First, we have to click the nominal point, and afterward the corresponding actual point. So in this case, it's quite easy to click this point here, for instance, as the nominal point, and use this one over here as the actual point. We're going to do the same thing for this point over here, which is this one. And this one belongs to this one. And as a third point, we can use this point over here. If I now show this cut file once again, you can see that now the cut data is aligned properly to my point component, or the other way around. The point component is aligned perfectly to the cut data, and I have a very nice coordinate system. One thing that you need to know, we have different stage behaviors for the transformation. We have two modes available. One is the separate stage transformation, and the other one is the global transformation. The difference between those two transformations is a different transformation throughout the stages. If I have a global transformation, I just set my coordinate system to a specific position, and I'm still able to see the global motion during my deformation. If I use the separate stage transformation, I already apply a rigid body motion compensation on my project. For you to understand this a little bit better, if you have sorry, if you have a soccer ball and you shoot that soccer ball through your measuring volume, if you do a global transformation, you set your coordinate system very perfectly, and then using the global transformation, you will still be able to see the global motion of the soccer ball. So the soccer ball is still flying through the measuring volume. If you use, in this case, a separate stage transformation, the soccer ball will be fixed into the coordinate system, and you only see the local deformation of the soccer ball. The entire global motion is already removed from that motion overall. For deformation projects, like this one that we have here with the excavator, it makes absolutely sense to first start with a global transformation, because then we're still able to see what happened during the process of my testing. So if I go through the stages now, you see that I have my coordinate system over here, and the coordinate system is always on the same spot. If I take a look closer, I can see that the undercarriage is moving slightly during the digging process. So if I don't want to see this motion, I can apply a so-called rigid body motion compensation to my project. This is done also via I-align, and I go to rigid body motion compensation, and I have two modes available. One is transform by component. That's the one that we are going to use. The other one is the interstage pre-alignment. Interstage pre-alignment is something that you would use for ATOS trend projects when you have multiple meshes and you want to compare those meshes. For deformation projects with point components, it's absolutely useful to use the transform by component functionality. So I click there. I will call it rigid body motion compensation by undercarriage. Of course, here I have to pick the undercarriage as the component, and I click OK. What I can see immediately in my alignment explorer over here is that I still have the sensor coordinate system as the initial alignment, so I can always switch back to that alignment, and I have done the 3-point alignment over the cut file over here, and this is the alignment that I'm actually using. What I also have is a rigid body motion compensation by the undercarriage. What we see now, if I flip through the stages, you can see that the global coordinate system is now moving a little bit. You can see this quite nice here during the digging process. If you take a closer look on that line over here. If I flip through the stages, you can nicely see that the global coordinate system is now moving a little bit. To make this a little bit clearer for you, what rigid body motion compensation really means, I will create a second rigid body motion compensation, go to I-align, rigid body motion compensation, transform by component, and in this case, I want to do a rigid body motion compensation over the bucket. So I pick the bucket in here and click OK. I will show the cut file once again. I will leave the image mapping because now I will show you what does that really mean for our data. You can see the components over here. You can see the undercarriage cut file over here. And if I go to the Alignment Explorer, you can see that the rigid body motion compensation by bucket is now activated. You can have multiple rigid body motion compensation, but only one compensation can be active at a time, or none. In this case, we're going to use this by bucket. And if I flip through the stages now, you can nicely see that the bucket is still fixed, but the other data is moving. So that means if I want to evaluate relative motion between different components, I can pick every component as a fixed component and evaluate only the relative motion of the other ones to this component. If I turn on the image mapping once again, what does that mean here? This is the beginning. Once again, the bucket component is fixed. If I go to a different stage, you can see, of course, we can't change the image, but with the bucket moving in the image, also the global coordinate system is moving. If I go through different stages, you can see this nicely over here. So, of course, in this project, it doesn't make too much sense to use the bucket as a fixed component, so I will switch back here to the undercarriage. If I go through the stages, you can see that we are back on track again. All right. Now we can start evaluating our data a little bit. In this case, I want to evaluate the relative motion of the superstructure to the undercarriage. One easy way is just to go to the components, select the superstructure, and then use INspect to evaluate vector fields. So if I select the superstructure, I can either go to INspect over here or push Control and right mouse button and show the displacement. In this case, I would use the displacement in Z direction because our data is, of course, aligned here. In this case, this is the Z direction, and this is where the most interesting motion between those two components will happen. So I go to displacement in Z direction. I don't need tolerances in a deformation project. Click OK. And if I go now through the stages, you can see nicely what happens during the digging process and afterwards during the rotation just in Z direction between those two components, superstructure and undercarriage. You can also see that the legend has different values for all the different stages. You can change this by clicking on the legend. You have the scaling, and in the scaling you have two modes available, all visible stages or current stage. I will just turn off this one over here, because now I have a nice color range over the entire legend. And the difference between all visible stages and current stage is, if I go to all visible stages, the legend calculates these extreme values, here in this case 1.27 millimeters down to minus 3.51 millimeters, through all the stages that are visible in the timeline over here. If I click once again on scaling and would just show current stage, the scaling changes from stage to stage. I will leave it as it is for the moment, and arrows or vectors are quite nice on those points. To help me a little bit to interpret the data, I can also use the deviation labels over here and construct deviation labels onto my vector field. So now I also have the values for the vector fields directly visible. As soon as I have evaluations or checks visible in 3D, which are computed over the entire stages that are displayed in the timeline, I have them also available over here in the diagram. If I open the diagram, you can immediately see that I have those three checks available over here. I can here, for instance, turn on the legend that I know which curve represents which picker. And I have also different options available. I can use the extremer, for instance, from the legend to be used also in the diagram. I can use the values from the 3D legend, and I can also use a second axis. For instance, if I have an angle check and a displacement, which has two different units, but I want to see the two graphs in one diagram, it absolutely makes sense to use a second y-axis to display both checks in the same diagram. You can also use different diagram distributions. That means the inspections that you have done in the 3D view can be displayed with the same unit together in one diagram. They can always be displayed separately. Display all of one element together in the diagram, or of the same type together in one diagram. These are the options that you have. Curves is something that you need only for curve evaluations. This is not useful at the moment for point components. Okay, here we are at the moment. So this is a first very simple evaluation of the data. What makes absolutely sense now is to create a report page over here. Therefore, I just click on this Create Report Page button over here. Use the report style deformation. Click OK. And I have, of course, different templates available, a title template, table of contents, just 3D view and diagram. And the most important thing here is 3D plus diagram, and this animated. I will use this over here. Now, I can align this image here a little bit better, just that I have everything in there. Say OK over here, so that's a nice report page. Call it Webinar Report. Click OK over here. And what the software is doing now is it goes through all the stages that are visible in the timeline and creates a video file from this. So what we have available afterwards, when the software finished the rendering, is if I go to the report workspace over here, I have my report page in here, and I can start a screen presentation, either from the beginning or from the current page. We only have one page available at the moment, so in here it doesn't matter. And we have the video already available as a screen presentation. Quite simple. Of course, you can't take your evaluation PC to every meeting room, so we have the option to export the report page as a PDF file. I will do this here and launch the PDF viewer right after the rendering. And as soon as the software finished everything and we have the export, we can see that we have that report page available in the Acrobat Reader. We have that over here. And now I just have to click on the report page over here, and I also have that video available in the Adobe Reader. That's a very nice new function. Of course, you can also use GOM Inspect, the free viewer of GOM Inspect Professional, to further evaluate your projects. This is also possible with deformation projects. Another thing that I want to show you is that we can also move meshes with components. Therefore, I will load the mesh of the revolving superstructure, and I will import this as a mesh. Click OK over here. Software imports that mesh now. You can see the timeline becomes yellow. That means there is something wrong in all the other stages. I will show you later what's really wrong. It already looks as if the mesh is quite okay aligned to my data, but if I take a look from above, you can see that those points are flying here a little bit, and the data is not really good aligned. So what we have to do is we go back over here into the image mapping. I will open the pip function once again. and I will put my mesh in here, because what I'm going to do now is I want to bring the mesh closer to my component points. This is done by selecting the mesh, going to Operations, Alignment, Single Element Transformation, and here use the 3-point alignment once again. Now you have to keep in mind, you want to bring the mesh closer to the component points. That means in this case, the component points are the nominal points, and the points on the mesh are the actual points. It is slightly different from the usual workflow, but that's just the way it is. You have to keep in mind you want to bring the mesh closer to the point component, and therefore the points of the point component are the nominal points. So you simply click this point over here, is maybe this point over there. This point over here might be this point there. And this one is maybe this point over here. If you forgot to click nominal points and actual points in the right order, you still have the option to say, I want to invert the transformation to make sure that I've done the right thing. In this case, this is not necessary, so I click Apply and Close. Close this one, show the mesh now, and you can see that now my mesh is quite good aligned to my point component. So fair enough for the moment. Still the timeline is yellow, so what does that mean? There's something wrong. Only first stage is okay. So if I click into a different stage, my mesh is gone. The problem that we have over here is that a mesh can only be visible in one stage. So this is the stage where we've imported the mesh. To make the mesh visible and usable throughout all the stages, I simply have to select the mesh as it's done over here. I go to Operations, Elements, Tag Element to Component. I use the component Superstructure and click OK. Now you see the timeline is white again. That looks good. And if I now flip through the stages, you can see that the mesh is moving with my component. And the mesh is now also available for further evaluations. If I want to click some analysis points, I can also use the points on the mesh. I don't have to click only point component points. I can also click points on the mesh. This is really nice. Of course, this supports my visualization. And to save some time, I will just open a project where I've done this already. Because in this project you can then nicely see we have the undercarriage as the cut body over here, we have the superstructure and the boom and extension arm and the bucket all as components in here. And if I flip through the stages, all the meshes are moving nicely with the point components. If I turn off the image mapping, you can see this even better. Oh, sorry. You can see this even better, that everything is moving nicely with point components. All right, now let's come to the new timeline. Before we had a stage explorer, now we have a timeline. What is the difference? The timeline over here offers me multiple functionalities. If I do a right mouse button click and say Manage Stages, I have this new Explorer window over here, and I have all the stages visible with all information that might be useful for me. The stages that are displayed here in this Explorer are also shown over here in this little window on the timeline. So if I flip through the stages over here, you can see that also this box is moving over the timeline. What kind of information do I have? I have the index, I have the name, I have the timestamp. This is important for me. And I have also a real timeline behind this timestamps. So what can I do? Of course, I can rename stages just by clicking on this button over here. I can delete stages, which should be, of course, the last option. because when you do something and you want to disable stages, use the disable functionality. That means if I select stages over here, I can go on this button over here and disable those stages. What does that mean? If I disable stages like the first 6 stages that I have here, because I made maybe just a couple of reference shots which shouldn't be inside my project afterwards, I can disable those stages, and if I click close, then those stages are not displayed any longer in the timeline, but the stages are still there if I need to check something or to construct something. If you delete stages, they're gone. If you disable stages, they are still there, but not taken into account for any further calculations. If you made something wrong, you can still say, okay, I want to enable those stages once again. What you can also do is, if you've selected a range of stages, you can say I only want to use every 2nd, every 5th, every 10th, every 20th stage, or you can even user define this, so every 235th stage should be used. This is also something that you can do. Here you can set a different stage as the reference stage. The standard for deformation projects is that the first visible stage is the reference stage. You can click on any stage and set the deviation reference to this stage. If you've done this and it was wrong, you can also unset the deviation reference stage. We also have nice features about the timestamp. You can edit a timestamp, you can sort by the timestamp, and you can set a new stage reference times. This is quite nice because if I say 100 milliseconds, this is actually where the test really started. I can just go there and say, okay, the stage reference time in this case should be 0 milliseconds. I click OK, and I have 0 milliseconds in stage 11 then. All stages before stage 11 will get negative timestamps. All the stages after stage 11 still have the positive timestamps. That's what we changed here. Then I already mentioned this real timeline behind the timestamps. Here you can enter time breaks on purpose. So you can set a time break and say, okay, this is where everything started. I want to have a time break over there. The software automatically identifies time breaks. If you did your project like measuring a couple of stages, then you have to change something on the setup. You went back, measured a couple of stages again, went back to the setup, changed something, and measured again. The software will automatically identify those gaps as time breaks, and you can use this to adopt stage ranges to those time breaks. So what is a stage range? I will just click close here. Now my project is a little bit messed up, but luckily we have the undo function, and I can go back to a state where my project was working properly. So what is a stage range? If I go to manage stage ranges, I can adopt stage ranges where something interesting happened. That means, for instance, if I take a look over here in this area from stage 95 to stage 115, I have the rotation process over here. So I simply select this area, just push the shift button and select this area, and I want to add a stage range. In this case, this is the rotation. All right, so I have this visible now in the timeline. Rotation from stage 95 to 115. It is visible, and we have the stage range over here. As I mentioned, we also have this button over here to adapt stage ranges to time breaks that we have in the other dialog that we have seen before. So this is really a quite nice feature, because if I go in here now and double click on that stage range, I have only this stage range visible over here in the timeline. So why is that nice? I can focus on a certain range of stages, so on a certain time range to evaluate my project. And if I create now a report and a video, only the stages that are visible are taken into account to create this video. So I don't have to create videos over the entire project all the time, but I can focus on certain areas where something might be interesting for me. Another nice feature over here is, if I create once again in this project the vector field, another nice feature here is the legend is also, when we change the scaling to all visible stages, it only takes the stages into account that are visible in the timeline. So if I focus on a certain stage range, also the legend is adapted according the values over here to that stage range. This is quite nice, as I think. So, as I said before, we want to do some more checks. And I want to start with the projected point distance. I will do this for all the stages, so I leave that stage range once again, go maybe to stage 1. And what I'm going to do now is, from the undercarriage, I will select all points of this element. Just do a right mouse button click on the component, click select all points of this element. Because what I'm going to do is, I will construct a fitting line in there. So I have the fitting line here. You can call it undercarriage line. Say create and close. And to have the same line in all the different stages, I will just select this line, go to Operations, Elements, and tag this to the undercarriage. Okay, so now I have this over here. Next step would be that I want to evaluate any point on the superstructure as a projected point to that undercarriage line. So what I do is I go to Construct, Distance, Projected Point Distance, and now I can click any point on the mesh over here and project this one onto the undercarriage line. Say create and close. I got this distance 1 over here, and once again, it makes most sense if we evaluate just the deviation in Z direction. So I go to check, go to distance Z, click OK, and also over here, as soon as I have a check visible in the 3D view, I also have this check visible over here in the diagram. If I flip through the stages, you can see that there is the change. And quite easily, we have created such a projected point distance. Make this invisible once again, because we want to focus now a little bit on absolute and relative angle change. Therefore, I will construct 2 point lines. So my line 1 will be between those 2 points over here. I can use the Smart Creation buttons over here, and the other one will be between those 2 points over here. Say create and close, and now I've got those 2 points, two lines available. Between those 2 lines, I want to create an angle now. Go to Construct, Angle, 2 Directions Angle. Click over there. Now I just have to select the 2 lines, and I have those buttons over here to change the direction to get the angle really as you want to have it, because I want to have the angle right down here. So I simply click those buttons, and now I got the angle that I want. So create and close. I don't need to have this line visible anymore because I want to focus on that angle. If I go back to I inspect, you can see now that we have inside the deformation skin 2 checks available. The standard check over here, angle and angle in the projected planes, and also the so-called interstage check. So what we have over here is more or less exactly the same thing, besides velocity and acceleration, of course. But what is the difference? So I will create an angle check once over here, say OK, and the same angle change over here in the interstage check. OK. 0, 0. This is still the same, but let's take a look inside the diagram. We'll make this a little bit bigger for you. The blue line that we have over here is the line that we've created with the standard check. That means we see the angle change with stage 1 as my reference stage. The yellow line represents the interstage check of the angle. Here we see the angle change from stage to stage. That means more or less that every single stage is a reference stage without creating every stage as a reference stage. So that's what the interstage check does. What's quite nice over here is you can also just select stages in here and also create stage ranges, because this might be an interesting stage range to take a closer look on. So what I'm going to do now is I just do a right mouse button click, go to Manage Stage Ranges, and I want to add this stage range because this is actually the digging process. Got this in here, and if I focus on that stage range and I click through the stages over here, I can nicely see that this is the digging process where the bucket hits the ground. Another nice thing is also, let's go back maybe to the inspection of that distance over here. Because what's quite nice is if you select something here in the diagram, you can see that we have, it looks like noisy data, but that's actually the real data. If we click F4 over here, you have the option, if you use the expert functions over here, we'll put that on the side over here, to adopt a filter onto the data. We have two types actually available. This is an average filter and a binomial filter. And as soon as I click on that filter and I have the size 1, you can already see that the data changes. Once again, size 0 means there's no filtering applied, although the filter average filter is set over here, but there's no filtering applied. It is a chronological filter. What does that mean now? If I go to size 1 and I am in stage 58, that means I take into account stage 57, 58 and 59 to calculate an average value for stage 58. So filter size 1 means one stage before and one stage after are also taken into account for the new value. Of course, you can enter quite high numbers and change the data from measured data to more or less calculated data. So be careful with the filtering, but you have the option to use average filter and binomial filter. All right. So I think that was quite clear. Filtering is possible, and the difference between absolute and relative angle change also is quite clear. Now, a very interesting feature is the 6 degree of freedom analysis. This is normally something that you do in every deformation project as soon as you use point components. So I will make all this invisible here, because we don't need this any longer, because we want to focus now on 6 degree of freedom analysis. How is that done in version 8? The first thing that you have to do is to construct a local coordinate system. You have different modes. You can use this by an orientation, you can use geometric elements, and the easiest way for me now is the 3-to-1 alignment. In the first webinar that's actually on YouTube available, you can see how all the other ones are working. So we use 3-to-1 to create a local coordinate system. Simply click a plane, in this case the Z plane, y-axis and the origin, and therefore we get the X orientation as well. Tag this to the component bucket because we want to have the local coordinate system moving with the bucket. And I click create and close, and I have my local coordinate system over there. I will make this a little bit bigger. The size is actually calculated automatically, but sometimes it makes sense to have this a little bit bigger for visualization purposes. So you can see already that my local coordinate system has a different orientation than my global coordinate system. This is absolutely okay. It is no problem. I want to focus here a little bit on this local coordinate system. It is quite obvious that during the digging process we will have a rotation around the z-axis over here. This is the normal process. This is the deformation or the motion that we allow during this process. The question is, do we also have motion around the y-axis and around the x-axis? This is something that we can evaluate now. We use I-inspect once again and check the rotation around x and y-axis. What we immediately get are those two rings here orientated around the y-axis, the green one for the y-axis and the red one for the x-axis. What do they display? They will display the actual rotation direction around the axis. So if I go to any other stage and go back in here again, you can see that we have the rotation around the y-axis in this direction and around the x-axis in this direction. There are two things that you have to keep in mind when you're dealing with local coordinate systems and you're doing 6 degree of freedom evaluations. The first thing is the positive rotation direction. As the right-hand rule from physics says, the positive rotation direction is counterclockwise. This is something that you have to keep in mind. The second thing that is important is the order of rotation. That means if you want to come from one coordinate system to the other coordinate system by rotations, it is absolutely important to keep in mind that implemented inside the software is the rotation order y, x, z. So when we do something, we have the angles and we rotate something. First, it's going to be rotated around the y-axis, then around the x-axis, and then around the z-axis. These are the two things that you have to keep in mind when you're doing 6 degree of freedom analysis. So also here, as soon as you have something visible in 3D, it is also visible in the diagram. And here you can also nicely see that there is some relative motion around the x and the y-axis during the digging process and during the entire rotation process, which is deformation that is not necessarily allowed. Since we already have two coordinate systems, we can also start to evaluate the position of the origin of this local coordinate system in relation to the global coordinate system. Therefore, we simply construct a two coordinate system distance. And here we now have to pick two coordinate systems. The first coordinate system is the reference coordinate system. For me, in this case, it makes absolutely sense to take the global coordinate system. The coordinate system 2 is the local coordinate system. I will pick this over here. Say create and close. And now I have this two coordinate system distance set up over here. Now I can check this. And what I do is I want to check the distance in x direction. Here I will check this against the fixed value 0. Say OK. I want to do exactly the same thing for my y distance and also for the z distance. What happens if I'm doing this? When I do it exactly like this, I get the exact position in x, y, and z direction of my local coordinate system inside the global coordinate system. So if I go to a different stage, also those values change. Once again, go over here, the values change again. So by doing it exactly in this way, I can evaluate positions of local coordinate systems inside the global coordinate system. It works exactly the same way for rotations. As a last feature for today, I would like to show you what we can do with trajectories. Therefore, I will just focus over here on the superstructure. I already applied the stage range rotation, and I also will focus just on this stage range. How can we use trajectories and the stage range to create the rotation axis of the superstructure? This is quite nice and quite simple, because I just have to select the superstructure. I can use then inspect over here and show the trajectory of all the points that are selected over there. You can see this now. If I turn off the image mapping and I take a look from top, we'll also make the points a little bit bigger for you, that you can see this a little bit better. You can see now there is one point which is a little brighter. This is the point of the actual stage that I'm in. If I change to stage 95 again, the first point becomes a little brighter, and if I flip through the stages, you can see the actual position. So what we see is this is really a rotation that we are doing in this process. If I take a look like this, for instance, I will now simply construct fitting circles and use those fitting circles afterwards to create the rotation axis. So quite simple. I will select, deselect all, invisible. Okay, I select just those points over here and I get the first circle. I want to have at least 3 circles to have it a little bit more stable. Say create and close, and now I've got those 3 circles over here, and I have a basis to construct a rotation axis out of the center points of those circles. Those circles shall move with my component. So I go to Elements, tag element to component. In this case it's the superstructure component. Click OK. And I want to select all the points of this element. So now all the center points are selected of all the circles. Then I go to Construct, Line, Fitting Line. We'll call this the superstructure rotation axis. Say create and close. And this axis shall be converted to a nominal element without a measuring principle, because this is just the rotation axis for me. If I turn on the mesh now of the revolving superstructure, and I'll leave the image mapping once again, I will take a look from the top and flip over here through the stages, you can see that we have nicely created the superstructure rotation axis inside the stage range just by using trajectories. This is all that I wanted to show you inside the software. Another thing that I want to show you is a complete evaluation of this project, just to take a look for you how a nice report could look like. I have here the nice report. I will start a screen presentation out of this. I have here a nice title page. I have a table of contents. I have information about my component definition and my alignment to the cut data and the rigid muddy motion compensation by the undercarriage component. And then I also got my videos inside my report. This is the vibration of the superstructure due to the digging process, the distance between the point and the fitting line. Here the absolute and relative angle change of the boom and the extension arm. Got over here my local coordinate system with the evaluation around the two axes. And as a last one, also the superstructure rotation axis. And here the meshes quite nicely support my visualization of this report. So coming back to the presentation, you can download the version 8 software when you go to support.gom.com, download the software and go to GOM Software V8. There you're also able to update your license dongle. Also on the download software, we have a so-called What's New document available. This document shows you all the new features that we have available inside version 8 software. What's available under support.gom.com, manuals and tutorials. You go to GOM Inspect Professional, inspection manual, point inspection basic is the manual that guides you through all the steps that I've shown you inside this webinar. Let's take a closer look at this one. We have this point inspection basic manual available, and what we support in this manual is quite nice. If I go to page 27, we also implemented videos in the PDF file. So that means we have videos available that explain a little bit better what happens, what we are going to do, and what you see inside the software. Not only videos like this one, but also screen captures from the software. This is all that I wanted to show you today in this webinar. Now I just have to say thank you for your attention. I hope you enjoyed the webinar, and we will be available for questions for quite a while now. Thank you once again, and goodbye.